Today I'll be presenting our work, which consists in the simulation of production of a Patagonian wind farm using a complete model change, from the most simple and less computationally expensive tools to the most sophisticated ones. But what was our motivation? As you know, there is a boom in the construction of wind farms experienced in Latin America and all around the world. New computational tools can make a significant difference in the design, development, or expansion of wind farms, in particular in the estimation of the capacity factor, which is directly linked to the annual energy production. So by using these tools, we can improve the estimation of the capacity factor. So our purpose in this work is to address the capacity factor estimation by improving the wind resource assessment. And to achieve this goal, different wind resource analysis tools are used, with increasing spatial and temporal resolution and their associated phenomena. We are going to go to the most simple tools like reanalysis database. We are going to use the era reanalysis. Then we are going to do a dynamical downscaling with the mesoscale model WRF. And then we are going to introduce the wind turbines in a CFD model. We are going to use for that the OpenFOAM model to estimate the power production of this wind farm. So for this case, this is where we select the Manantiales Bear wind farm, which is a wind farm located in the Patagonia, Argentina. And we select this wind farm because this wind farm reported, and in its first 9 months of working, it reported a capacity factor of 62% in the monthly average and with maximum values of 71%. So as I said before, we conduct wind assessment with reanalysis with 50 kilometer resolutions. Then we perform dynamic and scaling with WRF simulations. We use 3 nested domains with a 2 kilometer resolution in the inner domain. And then with the wind roses coming from these 2 different sources, the reanalysis and the WRF results, we perform several OpenFOAM simulations, including the wind turbines in the model, to compute the power production. Here are presented the wind resource assessment from these 2 different sources of information, the reanalysis at the top and the mesoscale model at the bottom, and we can see how the wind speed distribution changes when increasing the resolution. So we can observe also that the mean values and also the wave parameters are in more accordance with the statistical ones reported for the WRF results. On the other hand, we can also observe in the mean wind speed fields at half height how the increments in the resolution can allow us to observe the local topographical effects impacting in the wind resource assessment. So this will lead to a more accurate, not also wind speed estimation, but also the wind direction estimation. Here we are also presenting the result of the OpenFOAM simulations for 3 different cases to understand how the wake can impact in the results. So we are presenting here the result for the most frequent wind direction, which is the west, considering 8 meters per second wind speed and 12 meters per second wind speed. So we can observe how the wake is more strong in the 8 meters per second case than in the 12 meters per second case, and this is linked to the fact that the thrust is higher at rated conditions. When the alignment of the wind turbine is produced, and this is produced when the wind is blowing from the north, we can observe a very strong wake impact, and this will lead to a very important reduction in the power production. Finally, we compute the capacity factor from the OpenFOAM results using the 2 different sources of information for the wind roses, the error analysis and the WRF mesoscale model, and we compute this capacity factor considering and not considering the wake. So we can observe also the wake impact, which is around 2%. This means that the presence of the wind turbine and the wake interaction in these wind turbines will reduce in 2% the capacity factor. And we can also observe in this table that the value for the WRF model, considering the wake effect, is closer to the reported by the wind farm than the one from the reanalysis. We also want to understand why these wind farms have such a strong capacity factor, such a high capacity factor. So for that we did this plot where we present the wind speed distribution overlap with the power curve for these wind turbines. So we can observe for the median that the median value is linked to the nominal power. So this means that more than half of the time this wind farm is working at the nominal power. This is why it has such a big capacity factor. Finally, I will say some conclusions. So the increase in the level of detail in the wind resource assessment improves the estimation of the average and well parameters of the wind speed distribution with values similar to the reported statistic. The capacity factor value computed from analysis data is lower than the reported average value, while the estimated with worse results is between the average and the maximum when the wake impact is considered. This is an important remark that it should be known that the calculation that we have done with the capacity factor was done assuming that all the wind turbines were operational during the whole period and responding to the power curve. If any of this assumption is not totally correct, it will directly affect the estimated capacity factor, reducing its value and bringing it even closer to the reported one. So thank you everyone.